Morning.
Good morning.
Very good morning. Nice to see that. Well, more than half of you are here. So this is supposed to be a joke right here. I've got a few announcements to make, but I hope you appreciate my nerdly humor. I found this rather fascinating. That the course has 115 people. That's the capacity, but 117 have dropped out. Yet there's 66 of you. That proves that you are all entangled. Now, if you don't see the humor on that, you might have trouble with this course. It's supposed to be funny, so please laugh. On sticking it out, you're past the day to drop courses, so you are the diehards. There's 66 of you, and you've kept up your bargain. You've stuck with it. You trust me. That's good. And my part of the bargain is to make the following few statements, okay? If you put the effort in, I mean, if you just do what you're asked to do, I guarantee those people will pass this course. Even if, you know, you're not doing as well as others who may be a little bit more better prepared or more adept at working on the kind of problems that we deal with here. Nonetheless, nobody will fail. There's been a few people that have been very concerned. Do I have a particular threshold? Do I have to have a quota of fails and all that business? No, I don't. And if I did, I wouldn't abide by it anyway. You know, the people that fail are the people that try to fail, really, in my classes. I think you all know that. So don't fear that so much. Also, another thing that's quite related to this is a few of you have been in touch with me about how to proceed along with the assignment. As you all know, I don't really give a lot of detailed instructions. It's because I want people to be free to think for themselves and independently and actually not fear the minutia of, did I do this right? Or is that what they expected? I don't play that game with you people. I want you to not fear, you know, some kind of tricky grading system. Aha, I gotcha. I don't do that. I instruct the TAs not to grade like that. I tell them to grade leniently. Obviously, this particular circumstance right now with COVID is really a special time. This is a special class. These are special times. So don't fear those things. Just enjoy, have fun, mostly with the programming part of the course. Is that clear to people? You know, I don't want that kind of environment where you're worried about things that keep you away from actually discovering things and enjoying this content, because it is a challenging course, to say the least. The material is different. It is very challenging. And on that subject, I've decided, even though some of you are very adept mathematically, all right, listen carefully, I'm going to de-emphasize the math. You know, in fact, I've already made it more than fair, because you're obviously going to have a 24-hour take-home midterm and final. And so there's really not much I can do as far as giving you really complex math problems, because you've got the answers to anything I would ask you. Does that make sense? Uh-oh. Oh, somebody's sad already. Well, I'm not saying I'm not going to give you the math, but I'm going to de-emphasize it in favor of the programming part of this course, okay, which is really what this course is supposed to be about. Okay, any issues about that or questions? How many people think that's a good idea?
I like it.
There's a lot of you are.
Sense to me.
Yeah, a lot of you, I expressed a lot of concern with the current PowerPoint when I sent it out. You know, it's heavy stuff. It really is. And it really isn't that bad, but it takes a long time to get used to it. And given the circumstances of this course being distance ed and all that, first time it's being delivered, I'm going to give you a real big break on that. I already knew I would. Okay, thank you. Okay, good responses, thank you. All right, constructive, and that puts me on the next issue. Only a few of you have sent me any constructive criticisms. Seriously, if you want to just send me, communications on anonymous Gmail account, I'm not going to go looking for you. You know, tell me how this course can delivered in a better way. Your constructive criticisms are actually of great value. Website, yes, we'd like that too. Well, actually, the website's that's a place where you can, have conferences like what we were going to do before. You want to? Okay, I'll set something up. Okay, good enough. No, there's no slides showing right now. No slides. Here, I'll put a slide up. All right. Okay. Let's have a look and see. Somebody claimed their Zoom is broken. How does that? Oh, by the way, I've emphasized here that I promise that it's clear that you put the effort in, you will not fail. All right. That's a promise. And if you're recording this, you've got it on video. Speaking of video, I just spoke with our IT people on SFU Zoom, and it is now available in a limited way. So this Wednesday, I'll begin recording, and they'll be uploaded to the SFU repository. Okay, so that's going to happen. I'm sorry it's taken so long. Another thing, too, that Microsoft video that's about 1 hour and 20 minutes long, make sure you watch that, okay? Make sure you watch it. I think I asked you to have it to have watched it by the end of this week, okay? Make sure you watch that because it is probably the best video on giving you a very, very broad but detailed enough introduction to know what it's all about, this quantum computing, without so much math, and but enough so that you get what's going on, because I definitely am delving deeper into it. But it's at the level that I want you to be at in order to understand exactly how it works, and with a really great example of an actual quantum computing algorithm. Make sure you watch it because it's going to help us in the next week. We're right now only behind about maybe 1 hour, especially if I de-emphasize the math. So any questions? Any questions at all? All right, then. Oh, no, not again. That's better. What's going on here? I seem to have trouble with my power cord. There we go. Okay, so let's just recap what we've done. All right. We are talking about vector spaces. I'm going to show you exactly what I think you should know. So in vector spaces, we talked about why we're using them is because a vector or array, on how pedantic we want to be, is ideal for representing the state of a physical system. And by using linear transformations, you can map out a transformation as in how this state function or a wave function in our case evolves with time. Given certain kinds of measurements and operators associated with that are these transformation matrices. And because it's a linear vector space, you can map anywhere in the entire space. It's incredibly powerful. And the way that's done is if you have this thing called an inner product, and that's based on having a norm. In other words, a measure of the length of a vector. And also, that's the norm. And some kind of geometric relationship, in other words, a projection of one vector onto another like a dot product. More generally, we call that an inner product. You're used to this idea of a cross product in linear algebra, of the other kind of vector multiplication. We're not going to do that. Ours is called an exterior product, which I'm sure very few of you have heard of before. We'll get to that. But it's a way of going in the other direction. What does a dot product produce? Well, two vectors can produce a scalar. And we want to go the other way. We want, a matrix transforming a vector into a larger space rather than a smaller space into a scalar. And so that's what we'll talk about today. It's called the outer product as opposed to the inner product. Once again, an inner product is nothing more than a generalization of the dot plot product. Norm is a big deal. The norm is, a measure of distance in your vector space. So we have these nice things. Now, we said that anything that satisfies so we have a transformation matrix on a vector producing another vector. In other words, a transformation matrix being some kind of a measurement operator produced on a state vector, in this case a wave function, to produce another wave function. So that is how the wave function evolves. And that's what we're doing here. So matrices represent linear transformations. This is all familiar to you. So anything that satisfies these properties right here is a vector space. And it turns out that functions can represent all these things. You can have a set of orthonormal functions, in other words, a basis set, say Euclidean 3 space. And in this case, it can be an infinite dimensional space. All it is an abstraction of what we already know about, say, Euclidean 3 space. That's all this is. Why? Because we can do it. And we can take all of this ammunition that we've built up over the ages of proof theories involved with vector spaces and so forth, and use it as a powerful arsenal to study these quantum mechanical systems. And so we talked a bit about what a vector space is, especially if it's complex valued. But I have a question for you. I think we left off here. Okay, we left off here. How can one measure the distance between functions? It's clear how you measure the distance between vectors, say. This vector goes to this point in space, this vector goes to this point in space. So you've got an idea of very simply how to measure it. In a Cartesian grid, you can measure things going the Manhattan way, which is up and down, right? That's the L1 way of measuring things. The L2, the least squares method, is just as, the straight line path as the crow flies, for two examples of how to measure in a vector space. But in a function space, well, this is, you don't have to memorize this. I'm just showing you how this works. Obviously, from basic calculus, from your introduction to calculus, you can see that this definite integral, just from its very definition, is good enough for measuring, say, what's known as the Manhattan distance. Okay, this is just the absolute value difference, meaning that's the distance if you go, rectangular fashion along with the streets. But if you want to go the way the crow flies, so to speak, that's the L2 norm, where this is a generalization, 1 over p. If it's a L2 norm, it's this thing squared, and that's called square integrable function. A square integrable function, we talked about that here. Square integrable. Yes, square integral functions. We talked about that. That pops out immediately from the Born rule. Remember, the Born rule is the fundamental proposition of quantum mechanics. The Born rule that you can have this probability distribution by, defined as a complex wave function, and its square produces the probabilities. So that in that case, with the complex valued wave function and its adjoint, you can produce these interference patterns. And just all it is a hack that just works. They came up with this because that's what the observations indicated, and this mathematical framework fits it. So don't think, where'd this come from? It's a hack. Everybody good with that?
Yep.
Good. Okay, so this is from your textbook, just so you don't think I'm going too far. This is the LP norm, it's called, the LP norm. So in other words, this is the square root of v squared 1 plus v squared 2. That is clearly the 2D Pythagorean distance, right? So that's what we mean by an L2 norm, where this is a square root, and that's what we use. Whereas, if you recall that slide earlier from, what's his name, that fancy guy. There he is. Yeah, this one right here. This guy right here, an equally important slide. Slide number 37 of this PowerPoint. That was Scott Aronson's Quantum Mechanics in one slide. Don't be sure to understand these two slides right here. Be sure eventually to understand, and you can see here that's an L1 norm, and this is an L2 norm. Okay, and all that means it's a measure of distance your system here in basic probability theory, it comes out as an L1 norm automatically, just as in quantum mechanics, it comes out automatically as an L2 norm, in this case, because of the Born rule. I think that's pretty easy to understand. Okay? So we did a review of these basic things. Remember this Born's rule in detail, you're not responsible for, but you can see at least here how the wave function times its complex conjugate, it works. It gives you this probability, okay? Satisfying probabilities properly. So, yes, let's just go on. The L2 norm is a Pythagorean distance. That's why we need a square integrable function, meaning that this integral exists. It's not infinite. That's what square integrable means. And we talked about what does continuous mean? We talked about a Hilbert space being a complete inner product space. Can anyone tell me what that means? These are the things I want you to know. What is a complete inner product space? Well, first of all, an inner product space is a vector space to which there is an inner product defined on it. In other words, you know, you've got a norm, and from that norm, you have an inner product. They are related to each other. And that simply means that you've got a measure of distance, norm, and, you know, a way of at least determining the projection of one vector onto another using the inner product in a generalized sense of the dot product. What does complete mean? Anybody, please? Anyone? Any one of you? 55 people. 57 are chatting. Holy. All right, whatever.
Does it mean continuous and differentiable?
Precisely. Precisely. So that we can apply this arsenal right here for it to be square integrable. So in other words, the fact that we can actually apply the limit. And that's what it's all about. It has to be continuous. So a complete inner product space is what we call a Hilbert space. That's all it is. It's a vector space that has an inner product defined on it, and it's complete. So I can apply the limit and hence calculus. That is it. You don't have to worry about that except for its definition. Now, as an anecdote, I had a graduate student in the math department, and we did some work on Hilbert spaces. And when it came time for his defense, the external examiner asked him, well, you know, you seem to be talking a lot about Hilbert spaces. What's a Hilbert space? And he just spent so much time on it, he forgot the obvious. And it was a little bit shocking. We passed him. But, I mean, to not be able to define the thing that you're working with, you people have to know what a Hilbert space is, okay? Let's not make that same mistake. All right, people? 65 people chatting. What the heck? Why? I don't get that. Whatever. You do what you do best. So this is how we measure in an arbitrary vector space. Ours is P equals 2, the L2 norm. And now, what does this thing mean right here? Well, this is a joke. This thing right here is a ket, as you know. A ket is supposed to be some interesting way of representing a vector in a Hilbert space. And of course, this is a joke on the Schrodinger cat. And we're just going to move on here. We talked about what a Hilbert space is already. Did we not do this? No, we didn't. We didn't do this, did we? I think we left off here. Did we not?
We left off on the difference between, or the distance between the functions.
Okay, good. That's what I thought. So Hilbert space, we talked enough about what it is. A Hilbert space is a vector space that has the structure of an inner product that allows length and angle to be measured. It's also complete, which means that the limit can be put on there. It's named after a very famous 20th century mathematician. So formal definition of a Hilbert space, okay, it's a vector space over the complex number C, okay? That's the designation for the set of complex numbers. And we denote them using Dirac's ket notation. It's actually called bracket notation. And so an inner product looks like this, whereas the inner product actually is an integral, okay? Bracket notation. I want you to get used to it, to know what it is. I sent you out a handout about it. That's about the most complicated business I'm going to force you to understand. I just don't want people to see a ket like this and not realize why that notation is being used. Everybody that studies quantum computing from computing science does not understand the meaning of this. And they just go, well, that's just convention. No, it's not. It's a very special, very important designation. It simplifies the mathematics so that you don't see a lot of complicated integrals and so forth. So I really want you to understand Dirac's bracket notation. Dirac is a famous figure from 20th century physics. Maybe some of you don't know who he is. He predicted antimatter, and he formulated one of the three ways of describing the dynamics of quantum mechanics, which is quite impressive. So an inner product is like the dot product between these two so-called vectors, the bra and the ket. That is an integral, okay? And so that produces a scalar, all right? And it has to be positive, it has to be linear, and never mind what skew symmetric means, that just simply has to do with a property that's useful in a Hilbert space. For example, when we're, dealing with complex numbers, and so that it makes things work out, say with Hermitian matrices, you get things that are physically realizable, like real number observations and so forth. So everybody knows what the complex conjugate is. That's pretty simple. It's basically the mirror reflection across the real axis and the complex plane of any complex number, right? So we've seen this before. This complex number reflected through the real axis of the complex plane is the complex conjugate. And this is the norm right here. This is clearly the L2 norm, okay? That's the L2 norm. You can see that this is the inner product of the state function with itself. And let's just see, again, back to the integrals. You can see when we're looking at square integral, that is this integral right here. That is exactly what we're talking about right here. So clearly, this is a lot friendlier notation. A lot friendlier notation right here. But that is to represent the L2 norm, okay? This is the norm that's used. It's complete, meaning that is an integral, meaning that the limit can be used. Does everybody get that? Is that difficult? Well, it must be, because people aren't saying anything, okay? This is something I want you to really focus in on. You know what it is? It's because in computing science, we don't emphasize calculus at all. That's one of the big problems with teaching this course. It's going to be really tough because you've all taken, what, 151 and 152, is that correct?
Yeah.
So you've had calculus 1 and 2, and you've never really seen, a lot of, how many people have seen the Fourier transform? Its definition.
Yeah,
Okay,
I've seen that.
Okay, so it's, there's some things you've seen, convolution, the Laplace transform, these things having infinite bounds on integration, which is something that not a lot of you may have seen in 151 and 152. Okay, it's something I just want you to get used to. Let's go back again and look at what this means, all right? So what this means is, okay, it means I've got an integral of this complex valued wave function, and its square integral means it's finite. That's all that means. And of course, what we really mean is we want the probability to be conserved, but it's got to be unity, right? But this phi with itself, phi squared is phi with itself. Do you see what I'm saying? It is this complex valued function times itself. And so that's what this is right here. It's exactly the same notation for that integral. And you take the square root of it. And you see that it's the same as this thing we're looking at right here. See, you take the square root of that thing and you end up like this is just the definition of the norm. All right. What else do I have here? Well, let's just leave it at that for now. Okay. Let's just leave it at that. This just represents the norm. Okay, that's the representation there. That's just phi with itself, and clearly that's an integral. We saw that from this this page right here out of your book. What the heck? What happened to it? Where's that norm business? Did I just, there it is. This thing here. All right. So that's where we got it from. Do you see it right here?
Yep.
Okay, that's the definition of the norm. And you can see where the square root comes from because it's an L2 norm. All right. So that's all this business is. Oh, gone too far. So given, sorry, God damn it. Oh my goodness gracious, have I gone too far or what? Okay, there we are. Sorry about that, people. So there, this is out of Preskel's notes. This is from Caltech. And these are really good notes. I'm showing them to you again. Complete inner product space, inner product that's complete. So you can see that's really, in a nutshell, what we mean by a Hilbert space. Do you see that, everybody? Complete inner product space. It's inner product. It's complete. That's the big deal right there. This is now from somebody else's notes here from CERN. If an inner product is introduced in a vector space, we can define the notion of orthogonality. And so two functions can actually be zero, okay? They're integral between the two, can be zero if representing perpendicularity, right? And so two vectors are orthogonal if their inner product is zero, just like if it's the dot product, you see? We also introduced the notion of norm using inner product. So the norm of some vector v, denoted by this, as we've seen, is obviously this deal. This is the L2 norm, and we've talked about this already. Normalized vector or unit vector is a vector whose norm is equal to 1. No big deal. A basis is said to be orthonormal if they're orthogonal and of unit length. You all know this already. All that's new here is that you can do it with functions. So what? That's the whole point. You can do it with functions. Now this bracket notation, all it is this thing that's in between this pipe and this angle bracket is a label for a quantum system. That's all it is. Now this is actually a vector in a Hilbert space. The magnitude of the ket is meaningless. It's because it's a ray. Never mind that for now. That's pedantic. I won't test you on that. Just call it a vector, everybody else does, okay? Because it just seems to make things simple. Now, what is Dirac notation? It simplifies all of this calculus. That's all it does. And it greatly simplifies it. I'll give you an example of that at the end. Any questions? Okay, so this is it in a nutshell. It's probably one of the best slides you'll ever see. Slide 118. States are represented by vectors in a Hilbert space, which is a complete inner product space. Observables are quantities which are associated with linear operators. So in other words, a matrix that operates on a state is an observable, and that's what causes the quantum system to evolve. Does that make sense to people? So when you observe it, something happens. It evolves. Remember, that's the wave function collapsing and so forth. Observations. Don't confuse that with transformations in the pre-observed state. You can produce transformations and evolve the state vector before you actually observe it, okay? Those are two different things, but they both are based on linear operators. So there's a measurement operator and there's the transformation operators that you use in your quantum circuit, you know, to evolve the state vectors and do it in such a way so that the interference patterns favor the correct solution on output. Of course, being probabilistic. Does everybody get that idea?
Makes sense.
Okay, okay, good. A bra is the conjugate transpose of a vector. So the ket is the vector. The ket is this thing. That's the bra, bracket, okay? So the ket is the vector. The bra is the conjugate. It's the complex conjugate of the conjugate transpose of a vector. The bracket is an inner product, therefore. The ket bra, that means I can put them together like that. That's the outer product, okay? The opposite of the inner product. Instead of the bra ket, it's the ket bra, which produces not a scalar as an inner product does, but a larger system, a larger Hilbert space of higher dimension. How many people are familiar with tensors?
A little bit.
Well, you know how, well, you think about it this way, and a scalar is a tensor of rank 0, a vector is a tensor of rank 1, and then a matrix is a tensor of rank 2, and it just keeps going on. These are, for example, these are kind of related. It gives you an idea. It's not the same thing, but it gives you an idea of these higher dimensions. So, for example, a vector clearly is something in physics that's used to describe, say, acceleration or velocity. On the other hand, you can have a vector that depends on another vector. For example, you can have a vector which represents the unit normal to a surface, and then another vector which represents some kind of a force acting on that surface. And so this is a relationship between two different vectors now, which now involves 9 quantities to keep in track of, and that is a rank 2 tensor. So you can see how you can go from a vector to a scalar with the dot product, and an outer product will take you from a vector to a rank 2 tensor. So these are higher dimensional objects. These aren't tensors in the same meaning, but it's related. What I'm trying to say is, if you have a ket by itself, that's a vector, a state. That is a particular state. Now, if you have these things represent, for example, qubits. If you have 2 qubits, now you have a higher dimensional space that's that you model them in using the outer product. And so 2 qubits gives you a higher dimensional Hilbert space that you're dealing with. N qubits gives you a dimensional space that's n-fold larger. Do you see what I'm saying? That's where we're headed. That's the purpose of the outer product. The outer product is to be able to deal with multiple qubits at the same time. And so far we're talking about qubits just being, you know, the wave function, a state vector. An operator is like a matrix. An operator acting on a state is like a matrix dot product, and the inner product is simply, that's the way we usually make inner product notation. We just simply have the ket bra, right? This is the, sorry, bracket, 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 bracket. You see that? This slide, number 118, you must make sure you understand. This is the easy way of seeing what Dirac's notation is all about. This is Dirac's notation for dummies, if you will. Sorry, I didn't mean anything by that.
So I have a question about that.
Yes.
I kind of haven't reviewed the bracket notation yet, but the bracket, the complex inner product, what does it return as a value?
What is it? What?
What does it return? Or kind of
well, inner product produces a scalar. It just produces a scalar value. That's it.
Is it for our sake, is it a scalar in the real numbers or in the complex?
Yes. All observables. Okay, that's an excellent question, and thank you for asking it. It actually reviews what we said before. Remember that there's 2 kinds of transformations. There are those that we use to actually collapse the wave function in terms of observing, right? Once you make an observation, it has to be a Hermitian operator. A Hermitian operator is one whose eigenvalues are real. In other words, like you just said, the observations, when we make observations, we're not observing complex numbers. Complex numbers are just simply a tool, just as the limit is a tool for dividing by 0 when you don't really do it, right? So a complex number is a tool, for example, for expanding and making the theory of polynomials complete. And similarly, when you're actually making an observation in quantum mechanics, you have to have a real observable. And that is done with using our Hermitian matrix. As far as making the transformations in the pre-observed state, you're using unitary matrices. You're using unitary transformations. Why? Because you want to preserve the orthonormal nature of these state vectors as you're performing these transformations on them in terms of gates, quantum gates. Do you see what I'm saying, people?
Yeah.
So the inner product Even though it is in a complex inner product space, it always produces a real scalar. Excellent question. Anybody else? We're getting close here, getting close. So here you can read this little blue thing. It's all review, the idea that that's a ket. And this is the bra. You see, it's the complex conjugate, okay? What does it say right here? Conjugate transpose, okay? So the asterisk means it's a conjugate, okay? It's the complex conjugate. That's what the asterisk means right there. And so the inner product produces a scalar. You can see how it works out simply, you know, by having this arrangement of remember the Born rule produces a real valued function. It's probability. And so that's why we use these complex numbers, and the complex conjugate with the inner product produces a real number, okay? Similarly, you can see how this works here. This is a row vector times a column vector. Well, the opposite right here for the outer product is a column vector times a row vector, which produces a higher dimensional system. We've got a one-dimensional system here producing a two-dimensional system, and that's the notation. It's a ket bra instead of a bra ket. Ket bra. Does everybody get this? Make sure you understand this.
Yeah, it's a tensor product from the lecture.
Exactly, exactly. Thank you. And here, that's from the textbook that you're supposed to read for. You're supposed to read for brain just shut off. You're supposed to read for the section 2.1 for our math section. This is the most difficult part for you to think about, okay? This idea that the inner product between these two, this is a operator on a ket, okay? The inner product between those produces this thing that's going to be important to us next week, which is called the, what's the matter with me? I can't even think about what it is right now. The statistical thing, brains shutting off, people. I'm sorry. We'll be looking at this next week. All right. So in direct
expectation value.
Thank you. Yeah, expectation value. And you can read this from that again. Well, Wikipedia has probably one of the better explanations of bracket notation. But I sent you one from someone, I think it's CERN, that took that and added some images to it as well. Whatever I sent you, there's an excellent explanation of how that works. So please study that. Please study this by looking at that handout I sent you. All right. So that is all a ket. That's what a ket is, right? And so that's what a bra is, okay? A bra is simply the complex conjugate, okay? And the complex conjugate, we call that the dual vector, okay? Dual space, so we're just reviewing again. Hilbert space, that's what it's called. If it's an n-dimensional Hilbert space, and it has an inner product defined on it. These are an norm. This is just reviewing once again with somebody else's notes, okay? And so the inner product is very simple. She's spelling it out, the actual mechanics of how to do it. I think this is an excellent review for most of you. Here's what she calls indirect notation, which we've already seen, the basic conditions of an inner product space. Again, there's the norm. Just, I think she has very easy to read notes. That's why I've used them again. The inner product defined from your textbook now, the math reference textbook. It's exactly the same, but in a slightly different explicit method. Nothing new here, except it's more formal. And this is the notation after having looked at what she uses. If you understand this notation, how it's done in the book, then you'll understand these kinds of problems right here. To verify that this thing just defined as an inner product is pretty simple. You just go through the mechanics of this. I don't think that anybody should have any trouble with these simple exercises at the beginning of the book. I mean, this is just your basic linear algebra that you've learned already. So I don't want to rush through this. It's just 10 minutes left. How about if we come back to that after you've worked on them? How many people have looked at these exercises and have no problems with them? And have you actually gone through and realized, oh, it's just basically these rules here with this notation, which is quite simple right here. I've got the inner product between this ket and this, the second argument, which is, from these definitions that we were talking about back here, it's exactly this interpretation, all right, of what each of these elements are. And oh no, I don't want to race through this. We're going to come back to this on Thursday. I'm racing through this. I can't do that. I'm going to go through this with you step by step. I have a feeling that some of you aren't sure yet. So let's leave exercises. I want to just finish this thing off quickly. We'll come back and do these exercises on Thursday, okay? I don't want to rush through it. We've got less than 10 minutes to go. So exercises here with answers. These exercises are all about manipulation of the inner product. That's it. And I think that this is pretty straightforward. I'm not going to ask you any kinds of questions that involve this kind of manipulation on any test in this class, right? I've already said that I wasn't going to do that, but you've got to walk through these to actually understand, clearly. I think some of you are a little confused still about, these basic notions. So we'll spend the proper time on Thursday. Fair?
Sounds good.
Okay, that's good. All right, thank you. So I just would like to finish this discussion. So the outer product, we know that what that is. Okay, this basically, is telling you you're going in the other direction. So in order to perform these operations using the laws of vector multiplication, you end up getting a larger beast, and you can see how that works, right? So it's V0, U0, V0, U1. So you can see how it's working. It goes across, and it goes across, and all the way down to the end. You see, that's the mechanics of the tensor product, or also known as the Kronecker product. And so that's what the notation looks like. But notice that I can take this outer product, and the result of that I can use. It'll produce another vector, which I can rearrange as a ket times the inner product of these two. The outer product is often used to describe a linear transformation between vector spaces, okay? That's the whole point is, I'm actually going from one vector space to another, and this always happens when you're having multiple states. A vector space defines one state. So if I have two state vectors, I'm going to have, like if I have two qubits, for example, I have to have a higher dimensional vector space, or at least different linearly spanned vector spaces to describe both of those independently, and they have to communicate back and forth via linear transformations. So rather than using inelegant transformation matrices like the one we did, a linear transformation from a Hilbert space U to another one on a vector row, on a row vector, in other words, a ket vector in U may be represented like that. That is simply all she's saying here, is that it is such a simpler way of describing it. It is so much simpler to describe than this right here. Okay, that's all she's saying. And so because this thing is commutative, that means, as always, that's going to produce a scalar. That's a scalar value right there. Everybody clear with this kind of stuff? So the tensor product, which you can see right here, you'll see this notation a lot. For example, the state 0 and the state 1 is conveniently represented by the state 0, 1 within the bracket, and that involves this outer product, which produces this larger Hilbert space. Now, here's something very important. We're going to see this next week. Pay close attention now. The inner product and the outer product are related to each other. It's amazing that most sources don't state this. They just talk about the trace immediately. The trace of this outer product is simply that inner product. In other words, what is the trace? The trace is just the sum of the diagonal elements of this outer product. And so, for example, the trace, well, that's all I just said. It is just the main diagonal of a square matrix, right? It is the sum of the elements of the main diagonal of a square matrix. So for example, if I've got this 1 by 1 as a scalar, which is produced by a 1 by n transposed matrix by an n by 1, which gives you this beast right here. Then I could represent it by this matrix. If that's the case right there, then going backwards, you can see by this n by n matrix, which is equal to this vector times its transpose, and have a look here, it produces this, okay, this thing's in the way. It produces the trace of the inner product is exactly this beast right here. So it's going from the outer product to the inner product. You see that? The relationship between the inner product and the outer product. That's the outer product. That's the inner product of these two vectors, if you will. And so you can go back and forth via the trace operation. And so this shows you right here how I can go from the outer product back to the inner product. The inner product, of course, producing a scalar quantity. And that's found right here in the diagonal, summed up, that's what this is, of the outer product. So the inner product and outer product are tied by this definition right here. Everybody good?
Mm-hmm.
Okay, you need to know what these things are. I'm not going to force you to do any actual calculations, but I want you to know what these are. I think I'm giving you all quite a big break here. I think I'm giving you a very big break. These are nice things to look at. Look at the remarks of the outer product on your own, all right? There's also properties. Linear operators here. This is the part I told you to look at for next week. And this is the part in that section of the Dirac's bracket notation that I want you to look at, which is used for the expectation value, okay? And there it is. This is the part I want you to read. That it's basically a function composition. Make sure you read this for Thursday, and we'll go back and look at all these problems that we just bypassed earlier, okay? This is a very nice set of diagrams that is in that bracket notation wiki PDF file that I sent out last week. Exercise, yeah, here, this gives you an idea of how simple stuff is here, all right? When you use Dirac's delta notation, we reduce, I'm rushing through this. This is an exercise to show you the power of the Dirac delta notation, the Dirac bracket notation. And so look at without using bracket notation and with using bracket notation. It's unbelievably convenient. So that's a good exercise, which we'll talk about as well. And I think we're done for now. See you on Thursday. Make sure you read that Dirac delta, Dirac bracket notation handout. And be sure to watch that Microsoft video. How about if anybody wants to have office hours, we do it in half an hour. I need a break. Sound fair?
Sounds good.
Yep.
Any questions? Are we doing okay?
Is there any chapter at the moment that you're suggesting we should be reading?
Well, you know, I am going to admit to you, I'm very sinful right now of not paying much attention to the textbook. I'm following through very roughly on what the textbook's about. I'd say focus on chapter 3. Let's have a look right here. I think maybe, oh, I don't have the thing here. Okay, it's not here. Let me just stop. Let's have a look here. Okay. There it is. Okay, so let's have a look here. Your screen, you. So this is